Oxygen. Oxygen was first prepared by Carl Scheele, a Swedish chemist, around 1777. The elemental nature of oxygen was established by Antoine Lavoisier in 1778. Oxygen is the most abundant element on the Earth's surface and can occur in nature in both its free and combined state. Most elemental oxygen is present as a diatomic molecule, two oxygen atoms covalently bonded together, known as dioxygen. Dioxygen is the form of oxygen required for respiration. Oxygen has three naturally occurring isotopes with mass number O16, O17, and O18. The O18 is radioactive and is widely used in studying the mechanism of organic reactions. Decomposition of oxygen-rich compounds. Compounds with large amount of oxygen, such as KMNO4, KClO3, KNO3, liberate oxygen when heated according to the reactions below. So, if I take any of these compounds and add heat, I get the decomposition of a potassium salt and liberated oxygen gas. Thermal decomposition of KClO3 can be done in the laboratory. A mixture of potassium chlorate and manganese dioxide as a catalyst in the ratio 1:4 is heated in a hard glass test tube at 420 Kelvin. Oxygen gas is produced according to the first reaction shown above. The oxygen gas is collected by the displacement of water. Oxygen can also be prepared by the action of water on sodium peroxide. Sodium peroxide is placed in a flat-bottomed flask fitted with a funnel and delivery tube. You can see the sodium peroxide here, the funnel and tube here. Water is added in small lots through the funnel on sodium peroxide. Oxygen gas thus liberated is collected by the downward displacement of water through the delivery tube here. Decomposition of metal oxides. The oxides of certain heavy metals, such as mercury, lead, and silver, upon heating, decompose to liberate oxygen gas. You can see these mercury and silver oxides. Upon heating, we get the free metal and oxygen gas. This is an electrolytic process which requires an inert anode that can continue to sustain oxygen evolution. A similar process on lunar regolith has been done in studies to be used as a source of oxygen on the moon. Liquefaction of air. The most economical method involves liquefaction of air, followed by the fractional distillation of the liquid air. This process can be done on a large scale. Since nitrogen has a lower boiling point, nitrogen gas will distill over, leaving behind the liquid oxygen. Properties of oxygen. Dioxygen, or O2, is a colorless, odorless, tasteless gas. It is slightly soluble in water. Even at a low solubility, there's enough dioxygen to sustain marine and aquatic life and the decomposition of organic matter. It can be liquefied to a pale blue liquid at 90.2 Kelvin and freezes to solid at 54.4 Kelvin. It is neutral to litmus. Oxygen is not combustible, but it is a supporter of combustion. A glowing wooden stick, when introduced into oxygen gas, will burn bright. The above method is used as a lab identification test for oxygen gas. Oxygen is a powerful oxidizing agent. It combines with a number of metals under different conditions to form their respective oxides. When combined with nonmetals, with the exception of noble gases, oxygen forms their oxides. Dioxygen is necessary for respiration. Oxygen is used in oxyhydrogen and oxyacetylene torches for cutting and welding of metals. It is used as an oxidizer in metallurgical processes. It is used for artificial respiration. Liquid oxygen is used as rocket fuel. You can see the ionization energy, electronegativity, radius, melting and boiling points, density, bond energy, and bond length. So a table of a series of physical properties of oxygen.